So, take a second, just look at a piece of gold.
Yeah, like whatever you have nearby.
Right, like maybe it's a ring on your finger, a necklace, or, even the microscopic circuitry inside the phone or whatever device you're using to listen to this deep dive right now.
Exactly. It just sits there. It's totally static.
Completely silent.
Yeah.
But to get that specific cluster of atoms into your hand, it literally required the most violent, apocalyptic explosions in the entire universe.
It's wild to think about.
Have you ever actually wondered about the literal journey of those specific atoms? Like, where did that exact piece of metal come from before it ended up just sitting there in your hand?
It's such a profound question, honestly, because the answer isn't just, a mine in South Africa or some riverbed in California.
Right.
The real origin story of that gold takes us back millions, sometimes billions of years into these extreme cosmic environments that just completely defy human comprehension.
Well, today's deep dive is basically an epic cosmic road trip. We are tracing the origin of heavy elements, specifically gold, from the vast, freezing emptiness of the universe into the fiery accretion disks of dying massive stars, all the way down to the literal dirt beneath our feet.
And we aren't just making educated guesses here either.
No, not at all. We are pulling together a massive stack of research today. We've got astrophysics papers on galactic chemical evolution from researchers like Cote and Siegel.
We're also looking at X-ray data from a Tokyo University study on the space between galaxies.
Right, plus some groundbreaking insights on multi-messenger astronomy from the University of Guelph, and honestly, some fascinating math from a Reddit Ask Science thread about Earth's hidden geological reserves.
I love that we're including that. But yeah, the mission today is to give you a shortcut to understanding this cutting-edge scientific debate over exactly where the universe's heavy metals come from.
Yes.
Because by the time we're done here, the way you look at a simple piece of jewelry or even how you perceive how rare gold actually is, it's going to be completely shattered.
Okay, let's unpack this, because before we can forge heavy metals, we have to understand the cosmic soup they float in, right?
You just set the stage.
Exactly. And to do that, we have to talk about the interstellar medium, or the ISM. By mass, the ISM is roughly 70% hydrogen, 28% helium, and about 2% what astronomers broadly call metals.
Yeah, and we should definitely clarify that right away, because astronomers have an incredibly quirky definition of the word metal.
Oh, it's so weird. Basically, in astrophysics, anything heavier than helium on the periodic table is a metal.
Right. Carbon, metal, oxygen, metal.
Definitely a metal.
And while that 2% sounds tiny, it is doing such crucial work. I mean, that Tokyo University study we're looking at, they focused on X-ray observations of the intracluster medium.
Which is what, exactly?
It's the unimaginably vast space between entire galaxies inside massive galaxy clusters.
Yeah.
And by looking at the specific X-ray signatures emitted by superheated gas, they found that metals like iron, oxygen, and magnesium are just scattered universally across these giant voids.
Just floating out there.
Stretching out for hundreds of thousands of light years.
Which is just a huge clue about our cosmic history, right? Because these metals didn't just slowly leak out of galaxies recently.
Yeah, absolutely not.
For them to be spread that universally across millions of light years of essentially empty space, there had to have been massive, widespread metal synthesis happening very, very early in the universe's timeline.
Exactly. The cosmos was cooking heavy elements almost right from the beginning.
But the scale of it is so hard to grasp. Like in our interplanetary space here in the solar system, there are maybe 10 to 100 particles per cubic centimeter.
Pretty sparse.
But in interstellar space, it drops to roughly 1 atom per cubic centimeter.
Oh.
And in intergalactic space...
This study was looking.
Right. It's like 1 particle per cubic meter. It's like imagining a massive empty sports stadium. And inside that entire stadium, there are exactly 3 gnats just flying around.
That is, that's pretty much exactly the scale we're talking about here. But if we connect this to the bigger picture, this insanely dilute dust is actually the starting point for everything.
Oh, so?
Well, over millions of years, gravity and turbulence in the interstellar medium caused these incredibly sparse drifting atoms to slowly pull together.
Okay.
They clump into dust grains and eventually into these massive, dense molecular clouds of hydrogen.
Oh, right. The stellar nursery.
Exactly. These clouds act as nurseries. They collapse under their own gravity, compressing until the core temperature gets so hot that nuclear fusion ignites, and boom, you have the next generation of stars.
But here's the catch with stellar fusion. Normal stars, even the really massive ones, they're great at taking hydrogen and helium and smashing them together to fuse heavier things.
Right, like carbon, oxygen, neon.
And eventually iron. But they hit a hard wall at iron. A normal star simply cannot fuse anything heavier than iron because the underlying physics just completely flip.
Yeah, this is a crucial point. Fusing elements lighter than iron actually releases energy.
And that energy pushes outward. Right.
Exactly. That outward pressure of the release energy is what holds the star up against the crushing weight of its own gravity. But fusing elements heavier than iron actually requires energy to be absorbed.
So the star's internal engine just stalls out?
The outward pressure drops basically to zero.
Gravity instantly wins the arm wrestle, and the star collapses in on itself, triggering a supernova.
A massive explosion.
So if normal stellar fusion stops at iron, how do we jump way down the periodic table to get the really heavy stuff? Like how do we get platinum and europium and gold?
You need a specific mechanism. It's called the R process.
Okay.
The R stands for rapid, so rapid neutron capture.
Wait, I need to stop you there because I really want to understand the actual mechanics of this.
Sure.
If you are just bombarding an atom with free neutrons, doesn't that just make a heavier, more unstable version, like an isotope of the exact same element?
Usually, yes.
So how does adding neutrons actually change an atom of, say, iron into a completely new element like gold?
That is the brilliant part of the physics here. Neutrons are actually unstable when they are outside of an atomic nucleus.
Oh, really?
Yeah. So inside the R process, an atom is packed with so many neutrons, so incredibly fast, that the nucleus becomes wildly unstable.
Okay, I'm with you.
And to find stability, those newly captured neutrons undergo something called beta decay. The neutron literally transforms itself into a proton, spitting out an electron in the process.
Oh, wow. And because an element's identity is defined by the number of protons it has.
Exactly. That atom has just taken a step up the periodic table. Bombard it fast enough, and the atom rapidly climbs the periodic table all the way up to gold.
So you need an environment with just massive amounts of free-floating neutrons and extreme violent energy to force this bombardment before the atom can just fall apart.
Right. And for decades, the astrophysics community debated where in the universe these extreme conditions actually exist.
Which brings us to a total revolution in how we observe the universe. Multi-messenger astronomy.
This is where that University of Guelph research comes into play. It's fascinating.
Yeah, because for centuries, humanity could only study the cosmos by looking at electromagnetic radiation, right? Light, X-rays, radio waves.
Just looking at things.
But in August 2017, we didn't just see the universe, we actually felt it.
The detection of GW 170817.
Yes. The LIGO and Virgo observatories detected gravitational waves, literal ripples stretching and squeezing the fabric of space-time itself, washing right over the Earth.
And these waves were generated by a neutron star merger.
So two dead, ultra-dense cores of collapsed massive stars.
Right, slowly spiraling toward each other and finally smashing together at a fraction of the speed of light.
Unbelievable.
And because we felt the gravitational waves, we knew exactly where to point our traditional telescopes to catch the light from the explosion. We used multiple messengers to observe the exact same event.
And when astronomers ran the spectroscopic analysis, breaking down the light spectrum from the explosion to read its chemical signature, they found the unmistakable fingerprint of the R process.
The data from that single crash is just staggering.
It really is. The calculations from the Cote paper show that this one collision produced between 1 to 5 Earth masses of europium.
Which is huge.
And an absolutely staggering 3 to 13 Earth masses of solid gold.
Just try to picture that.
Right. Take the entire mass of the planet Earth, multiply it by 10, and imagine all of that as pure solid gold just being blasted out into space.
That is the output of one neutron star merger.
I do have to push back a bit, though. Or, well, I guess I'm just stuck on the math here.
Okay, lay it on me.
If a single crash pumps out up to 13 Earth masses of gold, wouldn't a galaxy filled with hundreds of billions of stars be absolutely overflowing with gold by now?
It's a fair question.
I mean, space is vastly huge, sure, but the LIGO data suggests these mergers happen at a rate of like 320 to 4,740 per cubic gigaparsec every single year.
That is a lot of crashes.
Over billions of years. So why is gold still so rare in our daily lives if these cosmic factories are just churning it out by the planet load? Does the math actually add up to seed the galaxy with the gold we observe?
It's a crucial question, and the Cote paper tackles it directly using galactic chemical evolution models, or GCE.
GCE, right. What do those models actually do?
They basically run a massive simulation of the galaxy's history over billions of years. They plug in the estimated frequency of these neutron star mergers from the gravitational wave data,
Okay.
and they plug in the amount of heavy elements they eject. And what they found is that the rate of these mergers is actually remarkably consistent with the total abundance of heavy elements we actually see distributed in the Milky Way.
Okay, so the math checks out. Neutron stars are the undisputed gold factories of the universe.
Well, hold on. Science is always more rigorous than just a simple case closed.
Fair enough.
The Cote paper includes a really major caveat. While the broad observational data fits the simulation perfectly, when physicists try to prove this using theoretical calculations derived from the first principles of nuclear physics, it gets very, very murky.
What do you mean by murky? Like, where does the theory actually break down?
It breaks down at something called the neutron drip line.
The neutron drip line.
Yeah. We are talking about atoms pushed to their absolute physical limits. They are packed with so many neutrons they literally cannot hold a single one more.
Oh, wow.
Any extra neutron just grips right off the nucleus. And the problem is, we cannot replicate those extreme, deeply unstable conditions in a laboratory here on Earth.
So we can't test it.
Right. Because of that, our math relies heavily on theoretical models of how these exotic nuclei behave.
Gotcha.
So, while neutron stars are a fantastic candidate and the observational math aligns, the underlying nuclear physics has just enough uncertainty to basically leave the door open for another suspect.
Which brings us to the plot twist,
Right.
because just when the astrophysics community was ready to crown neutron star mergers as the definitive source of the universe's heavy metals, a new paper gets published that throws a massive wrench into the established timeline.
It really shook things up.
I'm talking about the 2019 paper by Siegel, Barnes, and Metzger.
Right. They turned their attention to a dwarf galaxy orbiting our Milky Way called Reticulum 2.
And what were they looking for there?
Specifically, they were analyzing the long-term chemical enrichment timelines of the stars there. And the data they gathered points the finger at a completely different cosmic forge.
Something called a collapsar.
Exactly.
Let's define exactly what a collapsar is. So imagine a massive star, right? Many times the size of our sun. But unlike a normal massive star, this one is rotating extremely rapidly.
Super fast.
And when it finally runs out of nuclear fuel, the core collapses inward and immediately forms a newly born black hole.
Right.
But because the star was spinning so incredibly fast, the infalling outer layers don't just drop straight down into the black hole.
No, they don't. The rapid rotation forces all that infalling stellar material to flatten out.
Okay.
It forms this swirling, incredibly dense, blisteringly hot accretion disk orbiting right around the event horizon before it gets swallowed.
And here's where it gets really interesting. Why does that specific disk matter so much?
Because the physical conditions inside that swirling accretion disk are just absolute perfection for the process. Yeah. The temperature and density are so unimaginably high that protons and electrons are literally crushed together to form a sea of free neutrons.
Oh, wow.
It becomes the ultimate neutron-rich forge. And as the black hole feeds, magnetic fields channel some of this material outward in these massive, high-speed jets, blasting the freshly forged gold and heavy metals out into the galaxy.
But here's the kicker, right? Collapsars are significantly rarer than neutron star mergers.
Very true.
Like, a very specific set of circumstances is required to create one. However, when they do happen, they eject vastly more R-process material per event.
Yes. The researchers calculated that despite how exceedingly rare they are, because their payload is so massive, collapsars might actually supply over 80% of the universe's entire R-process content.
Wow. So relying on neutron star mergers for your galaxy's gold is kind of like earning a steady, reliable paycheck.
Right.
You get a little bit at a time regularly over a long period, but a collapsar is like winning a massive multi-billion-dollar lottery jackpot.
That's a great way to put it.
The lottery win is incredibly rare. You might only see it once. But the payout is so huge that it accounts for 80% of your total lifetime wealth.
And this raises an important question about cosmic timing, which is exactly what the Reticulum 2 data highlights.
Timing? How so?
You see, neutron star mergers are a slow burn. You need two massive stars to be born. Both have to live their entire lives. Both go supernova without blowing the binary system apart.
Which seems like a miracle in itself.
Right, leaving behind two dead neutron stars.
Mm-hmm.
And then those two dead stars have to slowly, gradually spiral inward, losing energy via gravitational waves over millions or even billions of years before they finally collide.
That's a long wait. Meanwhile, collapsars happen to single massive stars.
Exactly.
And massive stars burn through their fuel very quickly in just a few million years. They live fast and die young.
Meaning collapsars could have acted as the primary cosmic forge in the very early universe.
Oh, I see.
They were the explosive lottery winds that seeded the early galaxies with heavy metals long before the binary neutron stars ever had the time to spiral inward and merge.
So the early universe gets front-loaded by collapsars?
Exactly. And then the steady paychecks of neutron star mergers keep the gold supply trickling in over the billions of years that follow. It's a dynamic, ongoing process spanning the entire history of the cosmos.
Okay, let's bring this all the way home. We have traced this star-forged gold from the swirling accretion disks of collapsars and the violent collisions of dying neutron stars, drifting across the Milky Way and eventually finding its way into the swirling dust cloud that formed our own solar system.
And eventually Earth, about 4.5 billion years ago.
Right. So how much of that cosmic gold actually ended up here?
This is where we turn to some really brilliant breakdowns synthesizing geology and physics, notably summarized in that Ask Science analysis you mentioned.
Yeah, the Reddit thread. It was surprisingly thorough.
It really was. So when we look at the Earth's crust, the thin, rocky outer shell of the planet where we live, the average concentration of gold is about 4 parts per billion.
4 parts per billion sounds incredibly tiny.
It does.
But Earth is huge. Take just the top 4 kilometers of the crust, for example. That is roughly the depth of the deepest, ultra-deep mines humanity has ever managed to dig in places like South Africa.
Right, our current physical limit.
So it's the absolute maximum of what is accessible to us right now. In just that top 4-kilometer layer, there is an estimated 6 billion tons of gold.
6 billion tons.
Yeah.
And to put that into perspective against human history, I mean, from the ancient Egyptians to the California gold rush to modern massive-scale industrial mining, humanity has extracted roughly 180,000 tons of gold in total.
Which means throughout our entire history as a species, we have only mined about 0.0003% of the gold that is sitting in just the uppermost accessible layer of the crust.
It's wild. A single average cubic kilometer of Earth's crust holds about 10 tons of gold.
10 tons?
Yeah. At current market prices, that is roughly $400 million just sitting in a random block of dirt.
But, and here's the brutal reality of economics, it costs significantly more than $400 million to dig up a solid cubic kilometer of rock, crush it all down to dust, and chemically extract those 4 microscopic parts per billion of gold.
Right. The energy cost completely dwarfs the value.
And it is the exact same story with the oceans. There are an estimated 10,000 tons of gold dissolved in the world's seawater.
But the energy and infrastructure required to filter millions of gallons of seawater just to extract a single ounce makes it completely financially ruinous.
We have this massive disconnect between physical abundance and economic reality. Functionally speaking, gold is everywhere.
It is.
It's in the dirt in your backyard, it's in the waves at the beach. But because it is so incredibly dilute, it is entirely economically inaccessible.
Exactly. We can only mine it, where specific geological processes like superheated hydrothermal fluids moving through fissures deep underground happen to concentrate that gold into dense veins over millions of years.
And if you think the 6 billion tons trapped in the crust is a lot, we haven't even touched on the most mind-blowing statistic of all.
Oh, this is my favorite part.
Because the crust is just the surface. When the Earth was originally forming, it was essentially a giant ball of molten rock, right? Kept entirely slushy and liquid by constant asteroid bombardments and intense radioactive decay.
Yeah, a total hellscape.
And during that molten phase, a process called planetary differentiation occurred.
Also known as the iron catastrophe. Because the entire planet was a liquid melt, heavy elements naturally sank toward the center of gravity.
Like oil and water separating.
Exactly. While lighter silicate rocks floated to the top to eventually form the crust. Iron and nickel, being incredibly heavy, sank to the center of the planet to form the Earth's core.
Right.
And gold, which is one of the densest elements in the universe, sank right along with it. Geophysicists estimate that 99% of the Earth's total gold inventory was pulled out of the crust during this molten phase and is now permanently locked away in the planetary core.
Thousands of miles beneath our feet. 99%.
Just to visualize how much gold that is. If you could somehow reach into the Earth's core, extract all the gold and bring it to the surface, there is enough gold down there to cover the entire land surface of the Earth. Every continent, every mountain, every valley, to a depth of 0.5 meters.
That is insane.
The entire globe would be knee-deep in pure solid gold.
So the entire history of human economics, every gold rush, every war fought over territory, the rise and fall of the gold standard, the vaults at Fort Knox, is basically just us fighting over the cosmic table scraps that didn't manage to sink.
Pretty much, yeah.
We are literally walking on top of a planetary-sized treasure chest that we can never, ever open.
What's really fascinating here is how planetary physics played a sort of cosmic trick on us.
How so?
Well, it took a cosmic byproduct, a heavy metal that is actually relatively common in the grand scheme of stellar evolution, and by melting the planet and pulling it into the core, it locked away the ultimate treasure.
Right.
The iron catastrophe is what made gold artificially rare and valuable on the surface of our world.
So what does this all mean? Let's recap this incredible journey. We started with the interstellar void, where atoms float a cubic meter apart in the freezing dark.
Yep.
We watched them get pulled together by gravity into molecular clouds, only to be violently smashed apart and rebuilt in the blazing, swirling accretion disks of collapsars and the apocalyptic, space-time rippling mergers of neutron stars.
Such an epic scale.
Those freshly forged heavy metals drifted across the Milky Way, eventually raining down into a molten, newly born Earth.
And then the final twist to the knife.
Exactly. 99% of it sank completely out of our reach into the core, leaving us fighting over the microscopic fraction left behind in the crust.
It really reframes the way you look at a simple piece of jewelry.
It totally does.
And I actually want to leave you with one final thought to mull over, extending beyond our own solar system.
Oh, I like where this is going.
So if 99% of Earth's gold is trapped in our core, and we've only ever touched 0.003% of what's scattered in our crust, consider the countless exoplanets orbiting other stars right now. What if there are rocky planets out there with completely different geological histories?
Yeah.
Planets that may be formed further out from their star or experienced less bombardment, meaning they never had a fully molten phase.
Oh, wow. If a planet never turned into a liquid melt?
The iron catastrophe wouldn't happen in quite the same way, meaning the heavy metals never sank to the center.
That would change everything.
Imagine an alien world where this heavy, unreactive metal remained heavily concentrated on the surface, as common and accessible as dirt or iron is to us.
Just laying everywhere.
What would an alien civilization look like, and how would their technology and architecture have evolved if their most basic, abundant building material was the heaviest, most brilliant cosmic bling in the universe?
That is such a wild thought to end on. So next time you look at that gold ring on your finger, remember, you aren't just looking at wealth. You are looking at the wreckage of dead stars, forged in the most extreme environments in the universe, and the sunken treasure of a molten world. Keep looking up and keep digging deep.